Alright, so today's lesson, we are again doing the dot product, but we are going to be doing it with algebraic vectors. So we started before with the dot product with geometric vectors, where we said the dot product of two vectors is just equal to the magnitude of both, the product of the magnitude of both, multiplied by the cos of the angle between them. Now today we're going to come up with more of an algebraic expression with the coordinates. And we're going to do that by starting with the cosine law. So let's imagine here we have two vectors, let's say OB, which we'll call vector B, OA, which we'll call vector A, and they have coordinates A1, A2, A3, and respectively for B. And they're at an angle of theta apart, connected tail to tail. So if we were to use the cosine law for this, we can figure out the magnitude of AB by writing the magnitude of AB squared equals the magnitude of OA squared plus OB squared minus and so on. Just our standard cosine law. Now, we also know that AB, right, we can calculate that by using the difference in the positions for B and A. So we do B1 minus A1, right? That's our x coordinate for AB. Similarly, B2 minus A2 is our y coordinate, and B3 minus A3 is our z coordinate. And then we can find the magnitude of that squared by using our Pythagorean theorem in 3 dimensions, and we just square and add each coordinate, like so, which I wrote in blue because we're going to use that later as we substitute it into a different equation. Similarly, we can write the magnitude of OA squared. Since it's A1, A2, A3, we just write A1 squared plus A2 squared and A3 squared, and the same thing with OB squared. And lastly, this right here is our equation for the geometric dot product, which equals A dot B. Now I'm going to take this and substitute A dot B back into our cosine law right here. So you can see it here, minus 2 A dot B. The magnitude of AB squared, which I have here in blue, I'm going to substitute back into the cosine law, which I have here. And similarly, the same thing with OA squared and OB squared. At this point, it's a messy equation. Here we have B1 minus A1 all squared. So we're going to expand and simplify this. And I have that written below. You can go over that yourself. But I simply FOIL each bracket. And there's a whole bunch of terms that we can cancel out. For example, here we have B1 squared on the left side, and we have B1 squared on the right side. So cancel them both out. The only thing we're left with is minus 2A1B1, minus 2A2B2, minus 2A3B3, all equals minus 2 times the dot product of A and B. Now there's a minus 2 in every term, so if I divide that out, we get our algebraic equation for our dot product of AB. So A dot B equals A1B1 plus A2B2 plus A3B3. And you can do the same thing if you have a dot product for two vectors in 2 dimensions. You just don't have your third z coordinates. Right? It would just be x1 y1 plus x2 y2. With 3 dimensions, you have that extra plus x3 y3. So let's look at an example. Here's example 1. Now example 1 says, given these vectors a and b, calculate a dot b. Okay, well, you can do a dot b. Now that's going to equal a1 times b1, so negative 1 times 3, that's negative 3, plus 2 times 4, which is 8, plus 4 times 3, which is 12. We add them all together, we get 17. Notice again, there's no vector component to that because your dot product gives you a scalar, which is why, again, it's also called the scalar product. Now I can actually use this to prove that distributive property that we went over yesterday. So we did the investigation yesterday, and we showed that it works in one example, but does it work in every example? So let's prove it. So I'll just do it in a different color. So what I'm going to do is I am going to work with the right side of this equation, knowing that vector A has 3 coordinates, A1, A2, A3, 1 in X, Y, Z, and the same goes for vector B and vector C. So if I were to write this, expand on this, let's do A dot B. So A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. And then I need to add our dot product for A and C. So similarly, A1, C1. This is why I chose different colors, because I'm running out of room. A2, C2 plus A3, C3. There we go. Now what I'm going to do is I'm going to collect like terms specifically for A. I want to pull A out. So let me pull out A1. So I have an A1 term here, and I have one here. So if I factor out A1, I'm left with B1 plus C1. I can do the same thing for A2, and I'm left with B2 plus C2. You might be able to see where this is going. And I can pull out an A3, which I'm then left with a B3 plus C3. And this is our dot product of A with the vectors B1 plus C, B plus C. So that does equal A dot B plus C. So left side equals right side. Distributive property works for any case. Lastly, new color. Let's go over example number 2. Now example number 2 says using these vectors A and B from example 1, find the angle between them. Now we can use the equation for the geometric dot product and simply rearrange it. So just as a reminder, here's our equation, A dot B equals the magnitude of A times the magnitude of B times by the cos of the angle between them. Now if I rearrange, I can solve for the cos of theta as the dot product of A and B divided by the product of their magnitudes. Now I've already solved for the dot product of A and B in part A, so I still need to solve for their magnitudes. So let me do that up here. The magnitude of A equals, and we're using our Pythagorean theorem, so minus 1 squared plus 2 squared plus 4 squared, and take the square root of all that. Move over, and we get the square root of 21. And we can do the same thing to find the magnitude of B. The magnitude of B is the square root of 3 squared plus 4 squared plus 3 squared. This gives us root 34. So now I can find the angle between A and B, because their dot product is equal to 17. And we know their magnitudes are root 21 and root 34. And that equals to cos theta. So take the inverse cosine, and we can get theta equal to 50.5 degrees. Alright, let's go over some examples next. So example number 1 says, for what values of k are the vectors A and B perpendicular? Well, remember, if they are perpendicular, their dot product is equal to 0. So let's find the dot product of A and B. So A dot B. Okay, so first we have, and we'll set that equal to 0. We have minus 1 times 3, so we have minus 3. 3 times k, so plus 3k. And negative 4 times negative 2, so plus 8 equals 0. And now we can just solve for the values of k. And so you'll get 3k equals, so that gives you 5. Bring it to the other side, and we'll get k equals minus 5/3. Now the next one, part B, says for what values of m are these vectors perpendicular? Okay, so just scroll down a bit. So let's do the dot product between x and y, and we'll set it equal to 0 since they're perpendicular, and we get m squared plus or minus 3m, and then minus 18 equals 0. So here we have a quadratic. We can see that we can factor that. So factoring it gives us m minus 6 and m plus 3. So we have two values of m that will make this work. One will be 6, and the other will be minus 3. Our next question, here we have a parallelogram, has its sides determined by the vectors a and b. Determine the angle between the diagonals. So this angle right here. So these are the diagonals of our parallelogram. So we want to know that angle right there. All right. Well, to do that, we're going to use our dot product equation. Let me just go to this side because I'm going to need some space. So rearranging the dot product, again, we have the cos, theta. But what are we going to take the dot product of? Well, these two vectors, the diagonals. If this is A and this is B, connected tail to tail, we know that red diagonal is A plus B. The other diagonal is going to be A minus B. So we want to take the dot product of these two vectors, A plus B, and A minus B. There. And then we're going to have to divide it by the magnitudes of both of those. So A plus B multiplied by the magnitude A minus B. Okay, so before we use that equation, we're going to have to figure out what these are. First, I'll do a different color. A plus B. To do that, we can just add the coordinates. We've done this before. So 6 plus negative 1, so we're going to get 5. And 1 plus 3 gives us 4. We can do the same thing for A minus B. We have 6 minus negative 1, so that's going to give us 7. And 1 minus 3, so that's going to give us negative 2. Alright, so we have those vectors, so we could take the dot product of them. We also need their magnitudes, so let's do that as well. Need a little more room. So the magnitudes of A plus B is the square root of 5 squared plus 4 squared, which is root 41. And the magnitude of A minus B will be the square root of 7 squared plus negative 2 squared, which is the root of 53. So now we have what we need. Let's go back to finding the angle. So the cos of theta equals the dot product of these two vectors, here and here. So we have 5 times 7, that's 35, plus 4 times negative 2, which is negative 8, all divided by those magnitudes, root 41 times root 53. 35 minus 8 is 27. Take the inverse cos of both sides. You'll get theta equal to 54.6 degrees. All right, our last example says find a vector or vectors perpendicular to each of the vectors A and B. Okay. Well, we don't know what this vector is. I'm going to go down here. So I'll rewrite what vectors A and B are. So A was 1, 5, and 1, and B is minus 3, 1, and 2. And we're looking for some vector, let's call it vector x, which has, well, some coordinates x, y, z. And it's going to be perpendicular to both A and B. That means that x dot A will be 0, but also x dot B will be 0. Negative 1, not 1. Alright, so let's do these dot products. X dot A, so we have 1 times x, which is just x. 5 times y, so plus 5y. And negative 1 times z, negative z equals 0. You can do the same thing for our dot product with x and b. Negative 3 times x gives us minus 3x. 1 times y, so plus y. And 2 times z is plus 2z. And that should equal 0 if they are perpendicular, which is what we want. Alright, so I need to solve these two equations. Let's call this equation 1 and this equation 2. And I'm going to start by taking equation 1 and multiplying it by 3. So that's going to give us 3x plus 15y minus 3z equals 0. And now I'm going to add equation 2 to that. So you can see when I do that, you have 3x minus 3x, so there's no more x terms, that's why I'm doing this. 15y plus y gives us 16y. And then minus 3z plus 2z is minus z, which equals 0. So this is telling us that z is going to equal 16y. And I can substitute this z equals 16y, do it over here, back into equation 1, which is here. So we have x plus 5y minus z, but I'm going to write z as 16y equals 0. So this is going to give us as x is 11y. That means our solution, which I will go back up here and write this, so I want to see the diagram. Our solution for x turned out to be 11y, y, and 16y. So there's really an infinite number of solutions, but the interesting thing that I want to point out, which we're going to actually use a lot later in this course, is if we have the vectors here, a and b, you can think of those vectors on a plane. And this vector is going to be perpendicular to that plane. Right? And so this is sort of a general solution to find a vector that is perpendicular to a plane. And I'm going to pause there because we're going to use that at a later unit in the vectors course.